Electromagnetic induction also has a part to play in making sure that the electricity that we use in our devices is suitable for those devices. Inside this plug there is a transformer. I've opened up a plug here so that we can see what one looks like. So I've taken this off and you can see there it is. That little tiny yellow thing there. It looks like a tiny little coil of wire. Well, in fact, it is. It's more than one coil of wire, it's two. So here I have a much bigger version of the same thing. Two coils of wire and somehow connected by some sort of big iron structure. So to understand what this transformer does, we need to understand a little bit about its design. So this is it. The design consists of two coils of wire. There's the primary coil and then there's the secondary coil. In the hole of the middle of these two coils, we're going to pass an iron structure. It's called the soft iron core. So what we're going to do is we're going to place the primary coil on one part of the soft iron core, and we're going to place the secondary coil on the other part of the iron core. To complete the circle of that iron core, we're going to put an iron block on the top, which we're going to just clamp into place there to hold it securely. We need to understand what's going to happen inside here. So one of the things I'm going to do is I'm going to pass an alternating current through this primary coil. And what we're looking to see is what we detect on the secondary coil. So let's have a go. So here we are running an alternating current through this primary coil, and it's registering a voltage of about 2 volts across this coil. And you can see that we're getting nothing on this secondary coil. If we place it on this iron structure, the iron core, what we notice straight away is that we now get some voltage on here. That though this is not plugged into anything, a potential difference now exists across this coil. This is even more exaggerated when I complete the iron core and make it a complete loop of metal. So what is going on here? The alternating current that is in this coil is 50 times a second changing direction. When the current goes one way through the wire, it establishes a magnetic field around the wire, and this we looked at with the right-hand grip rule. But if 0.02 seconds later the direction of the current changes around, then what's going to happen is, look at the curl of my fingers, the direction of the magnetic field is going to have to switch from being one way round to being the other way round. It goes from being clockwise on my hand to anti-clockwise, and it does that 50 times a second. Every time it does that, it has to re-establish the magnetic field and then restart it the other way. And that continual movement of field lines are going to have an effect on any nearby coil. So around here, created by that alternating current, is an alternating magnetic field. Now that magnetic field would be lost to the air were it not for this soft iron core. You see, this soft iron core magnetizes by magnetic induction very easily. It also loses its magnetism very easily as well. It means that 50 times a second, all of those field lines get channeled around the metal through the other core. And 50 times a second, the field collapses and re-establishes itself in the opposite direction. That continual cutting of field lines, changing of field lines through this second coil, creates the conditions for electromagnetic induction to generate a voltage in this second coil. And that is the voltage that we detect there. So why is it 2.2 volts on the primary and 0.94 on the secondary? Well, the amount of voltage we get induced on this depends upon the ratio of turns between the primary and the secondary coil. This is complex. What do I mean the ratio of turns? Well, each of these has a number. This one here has 250 turns of the wire in the coil. And this one here has 500 turns in that coil. And so what's happening is we go from 500 turns down to 250 turns. What's happening is the number of turns is stepping down, it's halving. And if we look at the voltage is also approximately halving. Now this tells us something, that we can make a prediction about the voltage of the secondary by understanding the ratio of turns. If the number of turns halves, then we expect the voltage to also halve. Let's look at that in formula form. Let's have a look at the basic design of this. The ring of metal that runs through it, we call that the soft iron core. And it's not physically soft, you can't bend it, it's really hard, it's iron. But we call it soft iron because that's a reference to its magnetic properties. It has the capability of creating a magnetic field through it and it rapidly changing. Its magnetic induction is very rapid. And so what it can do is it can establish a magnetic field that runs through it in one direction and then very quickly, in 0.02 seconds, re-establish it the other way, which sets up the condition we need for induction of a very rapidly changing magnetic field near this second coil. So, the two coils. We have the primary coil over here, and we have the secondary coil over here. Notice how I've drawn this wavy symbol here, and that's to demonstrate that this requires an alternating current. So this is an alternating current here, and that alternating current is going to be created by an alternating voltage. So what's going to happen is that the voltage is first pushing one way and then the other way, and the actual movement, the alternating current, is what is creating the magnetic field that goes through the iron core, which induces an alternating current in the second. So we're going to call it an alternating current just here. You might get that confused as to why we are therefore measuring the voltage. It's just easy to do so. The alternating current that is creating the magnetic field is itself created by an alternating voltage, and it produces an alternating current in the second one that we detect by detecting the alternating voltage that goes with it. It's a little bit out there, but you've got to bear with it. Now there are certain things we know about this. We could count how many times we have wound that wire around, the number of turns on the primary coil. And we call that number NP. And so let's write down what these mean one by one. NP it's the number of turns on the primary coil. We've also got NS. And you've got it, that's the number of turns on the secondary coil. Be really careful with your language. Quite often, we're talking about coils in electromagnetism. And in many situations, the number of turns on the coil is interesting to us. If it's just a straightforward electromagnet, having more turns on that coil will make it a stronger electromagnet, with everything else being the same. Here, the number of turns on each of these two coils is significant in what's going to happen to the voltage. But be careful that you don't say, in both of these situations, that you're changing the number of coils. I know what you mean. You imagined it you coiling it one at a time, but that's just not the words that we use in physics. We describe turning the wire into a coil. And you're not going to get more coils. There's only two. And you're not going to ever get any more. So always use the words, you increase the number of turns, or you're counting the number of turns. It's really important. You will lose marks otherwise. Now, over here, this alternating current is being created by a voltage, the voltage across the primary. So Vp is the voltage in the primary. It is that alternating potential difference which is making the current flow through that primary coil. Over here, we've got Vs, which, you got it, that's the voltage that has been induced in the secondary coil. So Vs is the voltage in the secondary. Sometimes you will see this notation being displayed slightly differently. Sometimes the primary is represented by a number 1 and the secondary represented by the number 2. And so it's like V1 and V2 and N1 and N2. We're going to stick with this because this is what the exam board use, using P and S to represent the primary and the secondary. How does this work? Well, what we found before was it went from 500 turns down to 250 turns. And so that made the voltage of about 2 go down to a voltage of about 1. And so you can see that that is experimental proof of this, the transformer equation. That N1 over, NP over NS is equal to Vp over Vs. There it is. Scary because there's 4 terms in this equation, but not really scary when you see how it works. For the example that we had in the other room, if the number of turns on the primary was 500, then the number of turns on the secondary was 250, and we had a voltage in the primary of 2, then what would be the voltage in secondary? And this is normally how these sorts of questions appear. 3 of the 4 pieces of information are given, and you have to work it out. 500 divided by 250 is simply going to be, it's going to be a fraction of basically 2 divided by 1. So it's 2. So we know that 2 is going to be equal to 2 divided by Vs. We actually calculated that part. So now rearranging this, we can do 2 divided by 2 is going to equal Vs. And so we can see that 1 volt is equal to the voltage in secondary, which is roughly what we found. So this equation enables us to see what the output voltage is going to be. Here in this configuration, we have 500 turns going down to 250 turns. The turns have gone down, and so has the voltage. So we describe this as a step-down transformer. So now I've swapped it over. I have 250 turns here and 500 turns here. The number of turns has gone up, and we can see that the voltage has indeed gone up. So this is called a step-up transformer. The two are different. Step down, the voltage goes down. The turns ratio goes down. Step up, the turns ratio goes up and the voltage goes up. How are we getting more volts on this side than that side? If we remember what voltage represented, it was the amount of energy carried per unit charge. How come they're now carrying more on this side? Have we created energy from nothing? Well, no, we haven't. You see, what's actually happened here is even if this was 100% efficient, the amount of energy on this side would only be equal to the amount of energy on that side. The amount of power, the energy delivered every single second to this side, would be the same as on that side if it was 100% efficient. So where is it getting all this extra voltage from? Well, it's actually borrowing it from the current. You see, if you remember, electrical power was defined as the current multiplied by the voltage. If the voltage has gone up, but the power has stayed the same, then it must mean that the current has gone down. So what we're seeing here is that the current in here has halved so that the voltage can double, and that has kept the power the same. Now this leads to some very dramatic effects. If we had something that stepped the voltage so far down, then what we might find is it steps the current really high up. And that is one of my favourite experiments that I need to show you. So what I have here is an extreme version of a step-down transformer. I've got a very large number of turns on here. I've got 500 turns on here, and I've plugged it straight into the mains, 250 volts. Now I've only got 5 turns on the secondary, which means it's going to step down that voltage by a ratio of about 100 times. Now if it does that, it means it's going to increase the current by 100 times. So much so that if I short circuit my secondary with this nail, I'm going to do it just by touching it across, then a current that is 100 times greater than the current here provided by the mains electricity is going to pass through this nail. Let's have a look and see how it goes. So this current here is creating all of these sparks because the current is so high it's actually fragmenting the metal. Now what that means, and what is amazing, is that we can actually express this formula in a different way. If the voltage steps down, the current's going to step up. And so how to rearrange it so that that is what occurs mathematically is in the following way. What we would need is still the number of turns on the primary and the number of turns on the secondary, but we would put that equal to the current in the secondary divided by the current in the primary, but only when 100% efficient. And that is an important detail. Any question that is asking you to do something with the current will first have to claim that this transformer is 100% efficient to start with. So look what happens. If we go from 250 to 500, then this is stepping up. The number of turns is stepping up. So what this equals to, this is 250 divided by 500, it's a half. We know that a half is equal to this, which means that the current in S and the current in P goes up with a ratio of 1 to 2. So what is going to happen is if the number of turns goes down, the current is going to go up with the same fraction. So this is going to require a little bit of practice, but I recommend that you have a go and then see that the stepping down of a transformer steps down the voltage, but it steps up the current. In the next video, we're going to actually have a look at how transformers are used.